Good evening and welcome to the fifth weekly interactive session of the NPTEL GATE series. I'm Naresh, a research scholar in the Department of Civil Engineering at IISc. So today we'll be looking at some problems in uh, reinforced concrete design. We'll be restricting ourselves to beams. Before that, if this is the first session you're attending, in case you are not attending the previous sessions, for your benefit, I can I can join this Google Groups. So whatever presentations I use, the recordings, all these I will be uploading to the this group. So you can review them after the meeting. And in case you have any doubts, you can post them right there. You can also suggest topics for the next session. Let me paste the link to this Google group in the Q&A section of this meeting. You can also paste it in the chat. So let us get started. In today's session, we'll be looking mainly at the design of reinforced concrete beams for flexure and shear. So we'll have a quick introduction to what are the limit states, the limit state design, the limit state of serviceability, and the limit state of ultimate limit state, which is also safety. We'll see what is the limit state method. We'll look at the design stress strain curve of concrete and steel, followed by the methods of analysis of RC beams for the moment capacity. But this will be looking only at the limit state method. We will not be looking at the working stress because that is rarely used in design today these days, except for deflection analysis. Then a few codal requirements such as the minimum tension reinforcement and etc. Because questions are being asked based on this in GATE. And we'll also look at design function. So these topics are selected based on the five GATE problems that we'll be discussing today. So ranging from 2014 to 22. So let us get started. What is the limit state method? So in the limit state method, we aim for both safety and serviceability. The limit state method identifies what are called as limit states. And what do limit states mean? Limit states is when is a point at which the structure stops performing as expected. So it may have various limits. So the structure fails to perform in certain aspects. It can be in the verge of collapse, which is called the ultimate limit state. It's ultimate limit state. The structure is at the verge of collapse, either due to stability issues or strength, or it doesn't have enough strength, or it is overturning or sliding, whatever. So it is on the verge of collapse. And we can have serviceability limit state. So in the serviceability limit states, the structure has either malfunction or causes discomfort to the occupants. For example, if a beam is deflecting excessively under working loads, under the service loads. So service loads are the loads that are usually expected on the structure. If a beam is deflecting excessively under service loads, people cannot occupy the structure anymore. It will cause cracking, it will cause leakage, it will cause cracking of the uh, tiles and etc. And it is also not aesthetically appealing. So even if the structure is safe, if it is not serviceable, it is identified as a limit state. So these two are independent, and the limit state method, which is what IS 456-2000 follows, requires us to satisfy both safety at the ultimate loads and serviceability at the working loads. So this is the key idea. And the design principle is what we call what is called the factored resistance is greater than or equal to the factored loads. So RD is the design resistance of whatever we are designing. It can be a beam, it can be a slab, it can be a column, it can be a shear wall or whatever it is. So RD is the resistance obtained for a member based on factored material strengths. In the case of reinforced concrete, we take the concrete strength, the factored uh, uh, strength of concrete as 0.67 FCK divided by gamma C. And for steel, so this is for concrete. And for steel, the strength is factored, the yield stress Fy is factored by a material safety. So these are called partial safety factors. Why are they partial? Because they apply only to the material, not to the loads. So you call these partial safety factors. They are applied to account for the uncertainties in material properties. So concrete is highly heterogeneous, so it is very difficult to have a good control of quality. So the strength that we measure on a cube may not be the same for all cubes manufactured from a given sample of concrete. So these are called partial safety factors, where the partial safety factor for concrete, the material concrete, the compressive strength of concrete is taken as 1.5, and the partial safety factor for the reinforcing steel is taken as 1.15. And the design loads and SD is the action coming onto the beam. So for example, RD can be the moment capacity of a beam and SD can be the bending moment coming onto a beam. So this is the action coming onto a beam, and this is the resistance of that structure of that structural member to the applied loads. So the action is computed based on factored loads. For example, one of the possible load combinations can be, which you often find, is 1.5 dead load plus 1.5 live load. So in this case, these are the partial safety factors for the load. So these are also partial safety factors for the load, and these are the service loads. So service loads are the loads that are typically expected during the service of the structure. But we also account for accidental overloading by applying this partial safety factor. These are not only accounts for the accidental overloading, but also for the inaccuracies in analysis and design. So we make various assumptions while analyzing the structure. Those can have some errors, and those errors are also accounted for by factoring the load by a number greater than. So this is all basic introductory stuff. Let us look at the stress strain curve of concrete. So if you take a cube and compress it, you take a cube of concrete, compress it between rigid plates. The standard cube 10 cross 10 cross 10 centimeters. And if you take it and compress it, the stress strain curve of concrete, which is obtained, can be idealized by a parabola followed by a flat region. So the cube strength is what we call as FCK. Something like this. So parabola extends up to a compressive strain of 0.002, and the ultimate compressive strain of concrete under compression for flexural applications is taken as 0.00. So this is the cube strength or the characteristic cube strength. So you all know what is the characteristic strength. It is not the strength that is not exceeded. That is, it is the strength below which not more than 5% of the samples fall. So that is the characteristic cube strength. But our columns are not cubes, so we look at what is called the cylinder strength, and that is roughly our 0.8 times cube strength. So this is the cylinder strength. But the cylinder strength is measured on small cylinders, but the structures are large scale. There are size effects. To account for the size effects, we have what is called the characteristic design curve. The characteristic design curve is something like this. And that is obtained by applying a factor of 0.85 onto the cylinder strength. So this is around 0.67 times FCK. So 0.8 into 0.85 is about 0.67, 0.68. So this is the characteristic design curve. Characteristic curve. But even that is not enough because we need to apply the partial safety factor. So if you factor it, if you divide it by 1.5, we get the design stress strain curve of concrete. And that is something like this. So this is the design stress strain curve of concrete. And this value is 0.447 FCK. When we analyze reinforced concrete sections, The stress strain curve that we assume for the strain for the relationship between the strains and stress in the cross section is actually this. The last orange curve is what we take for design purposes. So if it is a column, if it is a axially loaded column such that the entire cross section is subjected to uniform compression, then the strain should not exceed 0.002. And if what we analyze is a beam, or if it is a beam column where there is flexion along with axial compression, then the strain, the ultimate strain under compression is somewhere in between these two. If it is under pure flexion, we are allowed to go up to an ultimate compressive strain of 0.0035. So this is pure flexion limit, and this is pure compression limit. Right? So this is for the case of axially loaded columns. This is for pure bed. So these are some basic things. And similarly for steel, if it is mild steel, the stress strain curve is idealized as an elastic, perfectly plastic material. So this is stress, this is strain. And again, we have a factor of 1.15. So as I said, the yield stress is factored by 1.15. So this comes out to about 0.87 times. So this is the stress strain curve we take in case it is a for the reinforcing steel. So next step is to, and in the case of high strength, high yield strength bars, you don't have a sharp yield point as it is. We'll have some curve lengths. And the yield stress is taken at 0.002 proof strain. So it is 0.002 proof strain. At this point, whatever the stress is, that is taken as yield stress. And the design stress strain curve of steel is at 0.87 times 5. So that's all it is. This is for steel, and this is for concrete. Next, let us look at the flexural response of reinforced concrete beams. So there are various assumptions involved in analyzing a cross section of a reinforced concrete beam subjected to bending. What are they? As usual, beam theory holds. So plane cross sections remain plane and normal to the neutral axis and suffer no change in length. So and they remain undeformed and remain undeformed. So this is the usual bending assumption, the beam bending assumption. This is the Euler-Bernoulli beam theory assumption. Next, what do we? So a consequence of this assumption is that the normal strains in the cross section are linearly distributed. So if this is a cross section of the reinforced concrete beam, what happens is you have, after it bends, the cross section remains normal to the deformed neutral axis. So this remains 90 degrees. And as a result, since the straight line remains a straight line, the strain is something like this. So above it is compressive, below it is tensile. And the strain distribution in the cross section is linear. Next, the steel is perfectly bonded. What does that mean? That means the strain in steel at this level is exactly the same as the strain in concrete at that level. There is no slip between the steel rod and the concrete that is surrounding the steel at that level. So otherwise, so these are the basic assumptions. The other assumptions actually depend on which method of analysis we are doing. So if you are doing a working stress analysis, then we follow that the stress, the concrete behaves in a linear elastic manner, and so on. But as I said, in this session, we look at the limit state method. So for the limit state method of analysis, the assumption is that the extreme fiber of concrete, the strain in the extreme fiber of concrete. So when I say concrete, we are obviously referring to the compressive strain because concrete doesn't have significant tensile strength. So under compression, is given by epsilon Cu is 0.0035. Why? Because when the strain in the concrete reaches 0.0035, according to this plot, it fails. That is the crushing strength of concrete under compression. So the factored crushing strength of concrete under flexural compression is taken as 0.0035. So this is the ultimate limit state of the beam cross section. Then what else do we assume? We also assume that so this is one thing. Then we assume that the section is cracked. By that, we mean the tensile stress in concrete is 0. Therefore, in the ultimate limit state, it assumes that the section has cracked everywhere below the neutral axis. So if you have the cross section like this with some reinforcement and the neutral axis somewhere here, only this section of concrete contributes to the bending moment at all. Below the neutral axis, the concrete will be under tension, but at very low tensile stresses, the concrete cracks and it cannot take any more stress. So the stress is below, stress is 0 in concrete everywhere below the neutral axis. So we only have a compressive stress above the neutral axis. And below, there is no tension in concrete, so we only have tension in the steel bars. This is the tension in the steel bars. This is compression in concrete. These are the basic assumptions. So the steps for analysis are as follows. So here are the steps for analyzing a cross section. There are only 2 steps. First step is find the location of neutral axis. How do we find the location of neutral axis? Neutral axis is what? Neutral axis is the line separating the region of tension and region of compression. So the idea is you assume that the neutral axis is located at a distance xu from the topmost fiber. And we also know that the strain at the extreme compression fiber in concrete is 0.00235, which means the stress above the neutral axis is just the full concrete stress strain curve. So this is what we had in the stress strain curve here. So when it comes to a section, since this is on a linear scale, it just gets rotated by 90 degrees. You just rotate the stress strain curve and put it up by 90 degrees, you get the stress distribution in concrete. That's all. So this is the stress distribution in concrete. We'll come to what it is. So this is a parabolic followed by a rectangle. This is the stress in the concrete, and we have strain. We also have the stress in steel, and that is tensile. So the stress in steel is tensile. So this is negative. This is positive. So if the section has to be in equilibrium, the compressive stress must be equal to the compressive force. The total compressive force should be equal to the total tensile force by sigma fx equal to 0 at that section. So this is what governs the location of neutral axis. So the total compressive force is what? It is the integral of the stress from 0 to xu. Integral of the stress from 0 to xu multiplied by the width of the beam. So just and that for concrete for usual and that is given as 0.362 times B xu. Right. So this is given by the code. It's a simplified procedure. So if you assume it is a parabola followed by a rectangle, if you do the integration, this is what we get. So it is 0.362 times B xu fck. So that is also given in, you can see in this question. So 0.362 times fck into xu into it's multiplied by the B. So this is the total compressive force. And what is the total tensile force? It is AST times the stress in steel fibers. That's all. The total tensile reinforcement area multiplied by the stress in the steel. So if it is if it's bending along only one axis, all the reinforcing bars will be subjected to the same stress. And how do we find FST? FST can be found by assuming a linear. So this is the stress distribution and this is the strain distribution. The strain distribution is linear. Take it like this. So the strain in steel at the level, strain in steel at this level is this epsilon ST. And the strain in concrete at failure at the limit state is epsilon Cu, because beyond epsilon Cu it will crush, the concrete will crush. So just solve this equation. This is known, this is known, this is known. How do we know FST? FST depends on FST is some function of epsilon ST. What is that function? That function is this. So we have this bilinear curve, and so if, and this is the yield strain epsilon y. This is Fy or 0.87 times Fy. This is strain in steel, and this is the corresponding stress. So if the strain in steel is less than the yield strain, you take linear distribution, and if it is greater, you take the it is plastically yielded, so it is a constant at 0.87. Depending on this, when the compression in the extreme fiber in concrete, when the compressive strain in concrete in the extreme fiber reaches 0.0035, if the steel is unyielded, we call it an over reinforced section. So if epsilon ST is equal to Fy and epsilon Cu is equal to 0.0035, sorry, if epsilon ST is equal to epsilon y, so it yields just at the point Fy is the yield stress, so this is the yield strain. So if this is simultaneously satisfied, what we have is a balanced section. So that is a very special case, but usually our sections are not balanced. It is not easy to design a balanced section. Why is it called balanced? Because yielding happens simultaneously. Failure happens simultaneously in steel and concrete at the same strain level. We also have what is called an under reinforced section, and all our beams must be under reinforced unless we have some, say, doubly reinforced sections or something. So when do we call under reinforced? When do we call a section is under reinforced? So the strain in steel has exceeded the yield strain of steel, and but the stress in concrete has reached 0.0035. So this is the most preferable combination. Why? Because steel is a ductile material. Even if the strain exceeds the yield strain, it is not going to break. The reinforcing bar will not break. It will elongate continuously. So it will give enough warning signs before the structure fails. So under reinforced sections are always preferable. And we also have over reinforced sections, where the strain in steel has not yet reached epsilon y, but the strain in concrete has reached 0.0035. This is extremely, so these sections are extremely stiff, and they do not have any warning signs before they fail because the steel has not yet yielded. It will just crush in a brittle manner. So these are not usually preferred in design of concrete structures. So then we have something called, let me. Okay, we'll come to one-way shear, but before that, there is one codal. So this is codal requirement. Let's suppose we find that the concrete, the moment is so low that the concrete alone is capable of carrying that moment without any issues, right? If we have such a condition that the forces on the beam are very low and the depth of the beam is so big that the concrete alone is enough. We don't really need steel. But even in that case, we have to provide something called the minimum tensile reinforcement. Minimum tensile reinforcement. This is typically asked in a one mark question in a grade. So minimum tension reinforcement is often provided. Why do we need to provide some minimum tension reinforcement? One reason is to arrest the cracks, cracks and things like shrinkage, and also to ensure that at the cracking moment we have, so at the moment at which it cracks, we don't have sudden jump in the deflection of the beam. So we to avoid things like excessive cracking, shrinkage, and so on, we need to provide a minimum tension reinforcement. How much should that be? So the minimum area of steel that should be provided in any case, regardless of how much the load, that should be so that divided by the product of the width and the effective depth should be greater than or equal to 0.85 times Fy of the steel. So this is important. The minimum tensile reinforcement should be so the minimum tension reinforcement should be at least the percentage of minimum tension reinforcement should be at least 0.85 times. So this you can since it's a minimum, we can replace it with an equal to. So the tension steel provided should always be greater than or equal to this value. And we also have conditions on deflection control. So in order to keep the deflections in the serviceable under serviceable loads in control, the code asks us to restrict the span to effective depth ratio to be less than or equal to 7 for cantilever beams, 20 for simply supported beams, and 26 for continuous beams. And these factors may be modified by the depending on the percentage of tension reinforcement provided. There is some modification factor KT and KC, and that will allow some increase in this because with reinforcement the deflection is better controlled. But those you may not be very much from a gate point of view because these requires certain tables and graphs to calculate. So this is enough for solving problems in gate. Mostly this should be enough. So that's all about analysis and the design of analysis of reinforced concrete beams for flexion. Coming to shear. So is there any doubt? If there's any doubt, I can clarify. Okay, please feel free to interrupt whenever you have any doubt. Don't have to wait. So under shear, what is the case? So we know that when we have a beam subjected to some forces, so we have the bending moment like this, and we also have the shear force something like this, depending on the same condition. So this shear, it tries to take an element of the beam. Suppose this is the shear in this case, it tries to deform the element of the beam like this. So the concrete, so if this state of stress you transform it to a coordinate axis like this, it causes tension in this direction, compression in this direction. So this is the case of pure shear. If you take an element along the neutral axis, there are no normal stresses. It is under pure shear. And if you transform the state of pure shear to an axis oriented at 45 degrees, you get equal and opposite compressive and tensile forces in the beam. And what will this tensile forces cause? They will cause the beam to crack like this. Therefore, if you have a simply supported beam, if you draw the direction of principal, so this is called the principal axis, right? So this is the major principal axis. Sorry, this is the minor. One of them is the major and the other is the minor. So since if we take compression as negative, this is the minor and this is the major axis. And if we plot the orientation of these axes along the beam, they will look something like this. So these are the compression trajectories, principal stress trajectories for compression. And these are the principal stress trajectories for tension. That is simple, right? It just means that along this line, if you take an element of the beam, the principal tension is along the tangent to this curve. And along this curve, you take an element of the beam. The principal compression is along the tangent to this curve, and principal tension is along the normal to this curve. That's all it means. So if the principal tension is normal to this curve, it means this is also a potential crack length. So if the beam is going to crack, it will crack along this length. So that is all it is. And so if you take an element here, which is very close to the neutral axis, as we already expected, it is oriented, the principal compression trajectory or the crack line is oriented at 45 degrees to the global x-axis. So we have which means the crack at this point will be something at like this, roughly 45 degrees with the horizontal. So when a beam cracks under shear, the crack lines will be roughly 45 degrees. So these are called web shear cracking or diagonal tension cracks. So the crack itself will not cause the beam to collapse because we have provided sufficient tensile reinforcement, but shear cracking reduces the flexural moment capacity. So once cracks are formed like this, that itself will not cause the beam to collapse, but that will reduce the flexural moment capacity of the beam. So the beam can collapse under flexion. So that is why it is important to design reinforced concrete beams under shear. And one-way shear is nothing but we have shear only in one direction. If you have a slab supported on a column directly, which is called a flat slab, that is going to punch the slab. So there you have shear both in this direction and also in the perpendicular direction. So that is something called two-way shear. And you can also have torsional shear. So those are the other types of shear. But in today's session, we'll look only at one-way shear, which is the usual shear that accompanies bending moment in normal beams. Right? Now, how do we design it? So the design for shear, they assume that the concrete has got some. So the total resistance of the beam cross section to shear has two parts. One part coming from concrete and the other coming from steel. For the concrete part, it is given as it is given from the code as so tau UC is some nominal shear strength of the concrete multiplied by the effective width of the beam multiplied by the effective width of the beam. So this is some nominal shear strength of concrete multiplied by BD. This is the resistance to shear force coming from the concrete. And to compute the resistance to shear force coming from the steel, they do some simple analysis like this. So they assume that there are lots of, so this is from Pillai and Menon, Reinforced Concrete Design. So it's a very good book. So it's very helpful. All basic and advanced topics are covered in a very nice manner. So you can refer to this book. I've also referred it in this slide. So everything I'm discussing in today is from that book only. So everything is from chapter 6 to chapter 3, 4, 5, 6 of Unikrishna Pillai and Devdas Menon's Reinforced Concrete Design book. So you can take a look at that book. It's a very good one. So the analysis is we assume that there are cracks distributed like this, and the shear reinforcement. Basically, our stirrups are provided like this. So our stirrups are oriented at some angle, say at some angle alpha. So the direction of stirrups is at some angle alpha, and the crack is oriented at some angle theta. In that case, what is the so if you take this distance, how many stirrups will be there? This distance is d cot theta. So if you take these two triangles, this is d, this is theta. So this distance is d cot theta, and this distance is d cot alpha. So d cot theta plus d cot alpha is this distance. And in that distance, how many stirrups we have? If the stirrup spacing is SV, we have the number of stirrups as d cot theta plus d cot alpha by SV. So many stirrups will cut through this plate, will cut through the crack. If you take a crack at an angle theta, so many stirrups will cut through the crack. And what is the force in the stirrup? Force in the stirrup is nothing but the force in one stirrup is nothing but 0.87 times Fy ASV. This is what does this assume? This assumes that the stirrup has yielded. Once the stirrup has yielded, the force is nothing but the stress, which is 0.87 times Fy multiplied by the shear reinforcement cross section, the shear reinforcement area. So this is the force in one stirrup. There are n stirrups. So what is the total shear force resisted by the stirrups? Vertical force. So this force is along this direction. So this is at what angle? This is making an angle alpha to the horizontal. We need only the vertical component of this force because the shear force is applied vertically. Therefore, the total shear resistance coming from the shear reinforcement is F sine alpha times N. That's all. So you just substitute everything. You get F is 0.87 Fy ASB. N is into D cot theta. I have sine alpha here plus cot alpha. Everything divided by S. And most of the cases, you can take theta to be 45 degrees and alpha, you usually provide vertical stirrups because inclined stirrups are difficult to construct. It's very difficult to place in construction. So we usually provide vertical stirrups. So alpha is 90 degrees, theta is 45 degrees. So VUS, the shear resistance coming from the steel is 0.87 Fy ASB. So sine alpha is what? Sine alpha is 1. Cot theta is 0 and cot alpha is 1. So we get 0.87 Fy ASB d by SB. So this is the shear resistance coming from steel, reinforcing steel, shear reinforcement. So that's all it is. Also, you have a B. So this multiplied by no, yeah, it's fine. So 0.8. This is having the units of force d by s. Yes. And again, as in the case of flexure, we need to provide minimum shear reinforcement. And the minimum shear reinforcement is given as the shear reinforcement ASP divided by the width of the cross section into the spacing should be greater than or equal to 0.4 times divided by 0.87 F1. So this is the minimum shear reinforcement that should be provided whenever the factored shear stress, so the nominal shear stress exceeds 0.5 times the stress of concrete, the shear strength of concrete. So the nominal shear stress in the beam cross section is given as Vu divided by Bd, the factored shear force divided by the area of the cross section, B multiplied by the effective there. That should be greater than or equal. If it is greater than or equal to half of the shear strength of concrete, if it is greater than or equal to half of the shear strength of concrete, we need to provide this much minimum. We don't provide shear reinforcement in slabs because typically the nominal shear stress in the section of a slab is less than half of the shear strength of concrete. So this is the minimum shear reinforcement. And this is the, so these are the basic things. So if there's any doubt, I can take. It's only one left, but if you have any doubt, please feel free to interrupt and ask me. So let us solve the problems. So consider this singly reinforced beam cross section. Stress block parameters are given, and we are asked to find out the moment of resistance for this section by the limit state method. So how do we approach this problem? As I told earlier, we'll start with determining the location of the neutral axis. So let us suppose that the neutral axis is situated somewhere here. Or no, they have already given the diagram. Right? So neutral axis is at this point at a distance xu from the top. We first need to find out how much this xu is. So the grade of concrete is M25. The grade of steel is Fe415. So how do we determine the location of neutral axis? So step 1, locate the neutral axis. How do we do that? The total compressive force should be equal to the total tensile force. What is the total compressive force? You can directly take it from, sorry, I have skipped the page. So locate the neutral axis. So the total compressive force, it is given as this. So if this is the stress distribution, they have already given the integral as 0.36 FCK times XU. So this is integral of this, but we need to multiply it by the width of the cross section. Therefore, it is the total compressive force is 0.36 FCK XU multiplied by B. And what is the total tensile force? So tensile force is FST times AST. Now assume that the section is under reinforced. So assuming that the section is under reinforced, FST is equal to, it has already yielded, so it is 0.87 times Fy, which is 0.87 times 415 Newton per mm square. What is AST? What is AST? They have given. We have 4 number of 12 diameter bars. So 12 bars. So the area of steel is 4 times pi by 4 into 12 square. So pi by 4 t square. And the area of steel comes out to be 452 mm square. So what is the total tensile force if the section is under reinforced? The section is, if the section is under reinforced, the tensile force is FST into AST. So just multiply these two, 0.87 into 415 Newton per mm square into 452 mm square. So this comes out to be, if you do the math, it turns out to be 163,335 newtons. This is the total tensile force. What is the total compressive force? It's given by this. So equate the two. The compression equal to tension. So in this case, what is FCK? FCK is given as 25 Newton per mm square. 25 MPa. So MPa is same as Newton per mm square. What is B? B in this problem is 200 mm. So just equate the two. So if you equate the two, you get 0.362 times XU. XU is given in mm into FCK, is 25 Newton per mm square, into B, which is 200 mm, is equal to 163,335 newtons. So if you take everything to the other side, you get XU to be equal to around 90.74. So we have done step 1. So what is the next step? So the next step is, okay, I didn't write it here. So the second step is compute the moment. So moment is equal to either tension into the lever arm or the compression into the lever arm. It doesn't matter. So in this, because both are equal and opposite, right? So the tensile force is acting somewhere here. Compressive force is acting here. How much is this distance? Let us call this distance as Z. So the moment in the cross section is nothing but the tensile force multiplied by Z or the compressive force multiplied by Z. So we have got XU. What is Z? The next step is to find this distance Z. So Z, as you can see from this diagram, total distance is D. This is 0.42 XU. So Z is equal to D minus 0.4. So this beam is actually under reinforced. If you take the ratio of XU by D, you take XU by D, if that is less than or equal to XU max by D, then you say the section is under reinforced. And XU max is given as some 0. The XU max is nothing but the neutral axis corresponding to balanced cross section. In that case, it is nothing but the ratio of strains. So 0.0035 divided by 0.0035 plus the strain in steel. The limiting strain in steel. And if this epsilon st, you can take it as 0. The proof strain plus Fy by E. 0.87 Fy by E. So compute this value, that will be the limiting XU max. So that is the value that should not be exceeded if the section is under reinforced. And in this case, it turns out that XU is less than XU max. So since this section is under reinforced, whatever we assumed is correct. Therefore, directly go to step 2. M is equal to tension times Z. Here the tension is what? 163. Already have 163,335 newtons. Multiplied by what is Z? Z is D minus X. What is D in this problem? X is 90.74. So find the product. This turns out to be about 42.7 10 power 6 Newton mm. It's nothing but 42.7 kilonewton meters. So the answer to this question, the moment of resistance for the given cross section by the limit state method in kilonewton meter is 42.7. So the correct answer is 42.7 kilonewton. So next question. This is a very simple question. We have a simply supported reinforced concrete beam. We have a simply supported reinforced concrete beam of span 10 meters. So the span L is equal to 10 meters. And it sags due to shrinkage. So there is some shrinkage happening in concrete. Because of that, it develops a curvature of. So there are no loads on the beam, but because of the shrinkage, it develops a curvature. Let us call the curvature as kappa, and that curvature is 0.004 per meter. And from calculus, you know, if this is the curve of the beam given as, say, y of x, from calculus, you know that the curvature is nothing but curvature is d square y by dx square by 1 plus dy by dx whole square over 3 by 2. But dy by dx is the slope of the beam. Under linear elasticity, the slope is very small, so this can be neglected. So the curvature is approximately d square y by dx square. And they said it is constant, assuming uniform curvature of 0.004 meter per meter along the span. You just integrate the two. So you get d square y by dx square is equal to 0.004 meter inverse everywhere. Now integrate once with respect to x, we get dy by dx is equal to 0.004 x plus c1. Integrate once again, we get y of x is equal to 0.004 x square by 2 plus c1x plus c2. Now, what are the boundary conditions? It is a simply supported beam. So y of 0 is equal to 0 and y of L is equal to 0. So enforce this y of 0 is equal to 0, which means this term vanishes, this term vanishes. It means C2 is equal to 0. And y of 10 meters is equal to 0. That gives 0.004 into 10 squared by 2 plus C1 into 10 is equal to 0. So if you rearrange, you get C1 is equal to minus 0.02. What are the units? It doesn't have any units because x is in meters, y of x is in meters, so C1 doesn't have any units. So the deflected shape of the beam is given by 0.004 by 2 is 0.002 x square minus 0.02 x. What are they asking? They're asking the maximum deflection due to shrinkage. So maximum deflection, they said it happens at the midspan. So just substitute x is equal to 5 meters, just L by 2. Substitute in this, you get the maximum deflection as minus 0.05. So the maximum deflection due to shrinkage is about 50 mm, 5 centimeters. So the maximum deflection in meters is 0.0. That's all. So going to the next question. A rectangular beam of width 230 meters and effective depth 450 meters is reinforced with 4 bars of 12 mm diameter. So what is the area of steel? It is the same as what we took in the first question. It is 4 times 5 by 4 12 square. So it is the same thing, 452 mm square. The grade of steel is 500, Fe 500. So Fy is equal to 500 Newton per mm square. Given that for M20 concrete, so FCK is equal to 20 Newton per mm square. And they are giving two scenarios. So when the percentage of tensile reinforcement, when the steel percentage is 0.25%, steel percentage 0.25%, the shear strength of concrete, the nominal shear strength of concrete in MPa is 0.36. And when the steel percentage is 0.50%, the shear strength of concrete is 0.48 MPa. Now, what are they asking? They are asking for a factored shear force of 45 kilonewton. So the applied shear force, the factored applied shear force is 45 kilonewtons. What should be the diameter of two leg stirrups if the spacing of the shear reinforcement is 375? So this is what is asked. We have stated all the data that is given in the question. Let us solve it. It's a very simple problem. So first question that we need to answer is, do we need shear reinforcement? So we know that we need shear reinforcement only when the nominal shear stress in the cross section, which is Vu by Vd, that is greater than or equal to 0.5 times the shear strength of concrete. So first we need to find out shear strength of concrete. So we are given that for 0.36 so when the steel percentage is 0.25, the shear strength is 0.36 MPa, and the steel percentage is 0.5, the shear strength is 0.48 MPa. So what is our percentage of steel? That will let us find out. So our percentage of steel is AST divided by BD into 100. What is AST? We already got it. It is 452 mm square. And what is the B of this cross section? 230 mm. D is 450 mm. So we have 230 mm into 450 mm. And you have an into 100 here. So the percentage in this case comes out to be around 0.436. So for this, you can do linear interpolation. So P is equal to 0.436. We have a P1, tau U1, tau UC1, P2, tau UC2. So you just linearly interpolate. You have 2 points like this. We know the shear strength and the percentage. We know at these 2 points. We have some point in between. So this is 0.25 and this is 0.5. At this point, we need to know what the value is. So this is P. Here it is 0.33, 0.48. So just interpolate linearly. So tau UC in our case is nothing but, so a left side value is 0.36 plus what is the slope of this line? 0.48 minus 0.36 divided by 0.5 minus 0.25 multiplied by what is this x distance? It is P minus 0.25. So it is 0.436 minus 0.25. What is this value? This comes out to be around 0.447 Newton per mm square. Next step is what is the nominal shear stress in the concrete. So nominal shear stress in the concrete is Vu divided by Bd. What is Vu? Vu is 45 kilonewton. So 45 into 10 power 3 newtons divided by Bd. What is Bd? 230 mm into 450 mm. So this is about 0.43 Newton per mm square. So if you compare, you see that tau B is less than or is less than tau UC. The shear reinforcement, we don't need to calculate any shear reinforcement. The shear strength of concrete itself is greater than the shear strength of concrete itself is greater than the nominal shear force coming onto the section. But that doesn't mean we need not provide any shear reinforcement. So we need to provide minimum shear reinforcement. Why? So minimum shear reinforcement to be provided. Why is that so? Why? Because tau b is still greater than 0.5 times tau uc. Right? Remember this condition which we saw here. We need to provide minimum shear reinforcement whenever tau, the factored shear force divided by BD is greater than or equal to 0.5 times tau uc. And how much is the minimum shear reinforcement? It is given by this. ASB by BSB is equal to 0.4 by 0.87 F1. So that's all. How much ASB we need to provide? So ASB required by B to SB is equal to 0.4 by 0.87 Fy. So just substitute all the values. ASB required divided by what is B 230, what is SV 375 is equal to 0.4 divided by 0.87 into how much is Fy? Oh, sorry, I was writing in the wrong page. Yeah, here. So ASB divided by B into SV is equal to greater than or equal to 0.4 divided by 0.87 Fy. So right hand side is fully no. What is this? 0.4 divided by 0.87 into what is the grade of steel? Grade of steel is 500 per Fe 500. Left hand side, what is ASB? So they're asking how many bars are needed. How many? So we have 2-leg stirrups. And what should be the diameter of 2-leg stirrups when placed at 375 mm? So there are 2-leg stirrups means you have this. So this is the cross section. You have 4 bars in the bottom, and the stirrup has 2 legs passing through the crack line. So that's why it's called 2-leg stirrup. So ASB is nothing but 2 times because of two legs are there. What is the area of 1 bar? It is pi by 4 d square. What is B? B is 230. SB is 375. Is equal to, so this is D required, is equal to 0.4 by 0.87 into 5. So rearrange, you get D required, D square required. If you see, if you take everything, so you'll get 230 into 375 into 0.4 divided by 5 by 2 into 0.87 into 500. So that comes out to be around 50.5. So take square root on both sides. We get D required is about 7.1 mm. So required is 7.1 mm, but we don't have a 7 mm bar. So provide D is equal to 8. So it is option A. So the correct answer is option A. So that's about it. Coming to this question. So this is also a very simple question. It's a very direct question. Can be so for a beam of cross section of width B is 230 mm. Effective depth is 500 mm. The number of rebars of 12 mm diameter required to satisfy the minimum tension reinforcement as specified by code is what? And they have assumed they have saying assume grade of steel as Fe500. So very simple. We already saw what it is. AST divided by BD should be greater than or equal to 0.85 times Fy. So this right hand side is 0.85 times 500, and left hand side is what? So we have n number of bars. N is what we need to find out. How many we need? So into pi by 4 times. The area of one bar is pi by 4 times 12 square. P is 230 mm, and D is 500. Just one equation. Take everything to the right hand side. You get n is greater than or equal to 1.73. You can provide 1.73 bars, so n is equal to provide 2 bars. So the answer to this question is that's. So here so it's a very easy question. If you remember this, it's just it takes only a few seconds to solve this question. That's so coming to the last question for the day. Okay, this is also a very simple question. In a reinforced concrete section, the stress at the extreme fiber in compression is 5.8 MPa. So we have a reinforced concrete section. The stress in the extreme fiber under compression. So assuming it is under sagging moment, the top will be under compression. The stress here is said to be 5.8 MPa. And note that they have asked us to assume linear elastic behavior of concrete. So do not take the stress block. So don't take the stress block. It is wrong. They have asked us to assume the stresses, the concrete is behaving linearly elastic. So in this case, you should take a linear distribution of stress. As I said, whatever is the stress distribution, just rotate it by 90 degrees and put it on the neutral axis. That will be the stress. So whatever the stress strain curve, rotate it by 90 degrees and put it on the neutral axis. That will be the stress distribution in concrete section. So since they are told assume linear elastic, it means the stress is very low. And as we can see, it is very low. So the grade of concrete is 25 MPa. So FCK is 25 MPa. But the stress is 5.8, which is less than FCK by 3. So it is still in the linear elastic range. So now the stress is only 5.8 MPa. You assume a linear distribution. The depth of the neutral axis in the section is 58 mm. So this is 58 mm. What is the effective curvature of the section per mm? How do we solve this problem? So first step is to find the strain in the section. So what is the strain in this section? Strain in the extreme fiber. So strain in the extreme fiber, let us call it a strain in the extreme fiber of concrete, epsilon C is equal to simple, just stress by Young's modulus of concrete. What is the Young's modulus of concrete? You know, it is given by 5000 root FCK. The short term Young's modulus is given by 5000 root FCK. So it is just 5000 into root 25, which is 25,000 MPa. So the strain in concrete is nothing but 5.8 MPa divided by 25,000 MPa. So this comes to around 2.32 into 10 power minus 4. What is so if you take two adjacent sections, what is the physical meaning of strain? So you know strain is if you take a fiber initially of length 1, this after deformation it's like this with a strain of minus 2.32 into 10 power minus 4. And below the neutral axis, you have some other strain. You have an initial fiber like this, and that extends to some other value. And the neutral axis is somewhere here. This is the neutral axis. Say x bar is 58 mm. What is the curvature of the section? So the curvature is nothing but this angle divided by the distance. So this is the angle subtended divided by this distance. And that is given as the curvature. Effective curvature is given as this angle by this distance. So if you take the strain distribution, this is the curvature. On both sides, they are equal. This is the compressive strength. This is the tensile strength. And this curvature is nothing but this epsilon c by x bar. So the rate of change of this angle is the curvature. This angle, if you take the deformed length itself divided by the neutral axis, will give this the rotation of the cross section. The rate of change of rotation is nothing but the curvature. This angle by this distance is the curvature. So this is phi by 2, and this is phi by 2. And this distance is xu. So phi by 2 xu is nothing. So this divided by xu is the curvature. And just substitute the values. 2.32 into 10 power minus 4 divided by 58 mm. So this comes to around 4 into 10 power minus 6 per mm. The curvature, effective curvature of the beam at that point is 4 into 10 power minus 6 per kilo. So it all corresponds to option number. Options. So that is the end of this session. Thank you for attending. Let me pause here for a while. If you have any questions, feel free to unmute us. Okay, seems like there's no one. So thanks for attending. You can review the videos and you can you can post your questions whenever you have. So thanks for attending. Hope it was very helpful. Let me end the session here.